You flip a light switch, and the room answers almost instantly. But the electricity that lights that bulb may have started many miles away at a dam. Before it becomes light, it begins as stored water held behind concrete under enormous pressure. That water contains potential energy, created simply by height, gravity, and mass. At a hydroelectric dam, operators control when that stored energy is released. When intake gates open, water is pulled downward toward the power plant below. It does not move through ordinary pipes. It rushes through giant steel passages called penstocks, built to handle extreme force. As the water drops, its pressure and speed increase rapidly. At the bottom, that force hits a turbine. A turbine is a large rotating machine with curved blades designed to capture moving water. In many American dams, the turbine is a Francis turbine, built for medium to high water head. In lower head plants, operators may use Kaplan turbines with adjustable blades. The exact turbine changes, but the job stays the same. Turn moving water into controlled mechanical rotation. That spinning turbine is connected to a shaft. The shaft enters the generator, where motion is turned into electricity. Inside the generator, coils of wire and powerful magnets move past each other in a precise pattern. That motion pushes electrons through the wire and produces alternating current, or AC power. In the United States, that alternating current cycles at 60 Hz. The generator makes electricity, but it is not yet ready for efficient long-distance travel. So the power is sent immediately to a transformer near the plant. A transformer does not create electricity. It changes voltage. At the dam, the voltage is stepped up to a much higher level to reduce transmission losses. That is why long-distance power lines carry electricity at extremely high voltage. Once stepped up, the electricity leaves the plant and enters the transmission grid. This is the part most people never see. Steel towers, insulators, conductors, relays, breakers, and control systems stretching across entire states. From there, grid operators begin their part of the work. They watch demand in real time and keep supply and frequency balanced every second of the day. If millions of people switch on lights, ovens, or air conditioners, the grid feels it almost immediately. Power cannot simply pile up and wait like water in a tank. Generation and demand must stay closely matched. As electricity moves away from the dam, it passes through substations along the route. There, transformers step the voltage down in stages for regional and local distribution. High voltage transmission becomes medium voltage distribution, the kind that can serve neighborhoods and businesses. Closer to your street, another transformer reduces it again to the level your home can actually use. In most American homes, that means 120 and 240 volt service. From the pole or pad-mounted transformer outside, electricity enters your house through the service line. It passes through the meter, then into your main breaker panel. From there, individual circuits carry power through wires hidden behind your walls and ceilings. Those wires are already energized and waiting at the switch box. When you flip the switch, you are not creating electricity. You are closing a circuit. That closed path allows current to move through the lamp and back through the system. If it is an incandescent bulb, a filament heats until it glows. If it is an LED bulb, a driver circuit controls current through semiconductors that emit light more efficiently. Either way, the result feels immediate. But it depended on a dam, a turbine, a generator, transformers, transmission lines, substations, and a stable electric grid. It also depended on real people: dam operators, control room staff, line crews, substation technicians, relay engineers, and maintenance workers. Most of them will never see your home. You will never see most of their work. But every time a dark room fills with light, their system has done its job.